Hello and welcome to the third lecture of this fourth module. In our fourth module, we have been discussing the macromechanics of lamina, wherein we have discussed strength failure theories or criteria of lamina. We have discussed independent theories as well as interactive theories, and then we understood the comparisons of different theories. So, till now in macromechanics of lamina, what we have discussed including the third module and in this module, we have actually developed the stress strain relationship for generally orthotropic lamina as well as for specially orthotropic lamina. Given the stresses, we can find out the strains and vice versa, and then using those stress strain relationship in terms of compliance matrix, stiffness matrix, or in terms of measurable engineering constants, we can determine the stresses and strains both with reference to the global axis as well as the material axis. Okay. And we have also understood the transformations of compliance and stiffness matrix from the local axis like material axis to global axis and vice versa. And with those stresses in the material axis, we understood in the last two lectures that how to apply appropriate failure criteria to assess the safety or failure of a lamina. So, today we will in this lecture we will discuss the hygrothermal stresses of lamina. Now, why hygrothermal stresses? In all our discussions till now, we have assumed that the composites are actually the lamina are actually does not have any environmental changes. Okay. There is no change in the environmental conditions in the lamina, but actually the composites are actually subjected to changing environment conditions both during initial fabrication and final use. Okay. Among different environmental conditions that influence the mechanical behavior, the change in temperature and change in moisture content are very important, especially for because we are discussing the fiber reinforced polymer composites. Therefore, for polymer matrix composites, these two have significant bearing on the behavior of the polymer composites. Okay. Now, change in condition may be during fabrication, like during fabrication there may be the composite or the lamina is actually cured at a particular temperature and pressure, and then it is allowed to cool down to room temperature. Therefore, there is a change in temperature. Similarly, when it is exposed to the ambient conditions, it may absorb moisture. Okay. Therefore, there may be moisture absorptions as well as temperature change. Also, in service, depending upon the service conditions, the operating temperature may be different from the ambient temperature, or the service condition may be such that the environment is humid and it may actually absorb moisture. So, in all these cases so there are two principal effects actually of temperature and moisture content on the mechanical behavior of polymer composites. Number one, the matrix dominated properties such as transverse strength and stiffness. What are matrix dominated properties? Matrix dominated properties, like I think we have discussed already, say the transverse stiffness, okay, then transverse tensile stress, okay, then shear stiffness, okay, or shear strength. So, these matrix dominated properties actually are significantly affected by the change in temperature and moisture content. Now, what happens is, as the temperature increases, there is a gradual softening of the polymer matrix till it reaches the glass transition temperature. If you look at this figure, now this is the stiffness versus temperature. So, as the temperature increases, there is a till this temperature, which is called glass transition temperature Tg. Okay. There is a gradual decrease in the stiffness. Okay. So, softening takes place, but after this glass transition temperature, the polymer becomes too soft and it behaves like rubber, now it is shown here, it is too soft like a rubber, and here it is like a glass, okay, and this is the transition region. Okay. So, beyond glass transition temperature, it becomes too soft like a rubber, it is not suitable to be used as a structural component, okay, structural material. In addition to that, absorption of moisture, okay, actually has an effect of reduction in glass transition temperature. You can see this is the dry glass transition temperature, and when it suppose it absorbs moisture, this is the wet glass transition temperature, which is less than the dry glass transition temperature. Now, what happens is because beyond glass transition temperature, this polymer is it is too soft to be used as a structural material, therefore, the operating temperature or the service temperature is kept well below the glass transition temperature, and when it absorbs moisture, the glass transition temperature actually decreases. Now, it is seen that these polymers are highly sensitive to absorption of moisture, sometimes maybe a 3 to 4% absorption of moisture leads to anything around 15 to 20% reduction in glass transition temperature. Okay. Also, you can see that suppose this is the stress strain curve at room temperature. Okay. This is the stress strain curve at room temperature. So, the slope is E1. Okay. Suppose if it is the longitudinal direction or depending upon the direction, this is the Young's modulus. Okay. Now, if it is at a higher temperature, you can see there is a reduction in the stiffness, okay, and there is a clear softening. Okay. If the temperature is increased further, there is further degradation in stiffness. Okay. And for the same temperature, if it is wet, its stiffness is even further degraded. Okay. So, both increase in temperature as well as moisture absorption has actually lead to the reduction in stiffness of polymer, and therefore, in a polymer matrix composites, the change in temperature as well as moisture absorption has significant bearing on the matrix dominated properties like transverse stiffness, transverse strength. And there is a second effect. Second effect is that because the fibers, because in the fiber reinforced polymer matrix composites, the fibers and matrix are having different sensitivity towards the moisture absorption as well as temperature. The fibers are not really that sensitive to temperature and moisture absorption compared to that of the matrix, and this results in a residual stress. I will come back to this little later. We will make a detailed discussion to understand what exactly is residual stress, but what is important is that the temperature increase as well as moisture absorption has two principal effects. Number one, that it actually the matrix dominated properties such as transverse strength, stiffness gets altered, okay, and then it leads to residual stresses are actually induced in the composites. Okay. Now, let us have a brief revisit of what exactly happens when because of the temperature increase. Now, we all know that in an isotropic material, that say like steel, suppose there is a increase in temperature, then what happens? There is a change in dimension, and the change in dimension is actually proportional to its initial dimension as well as the increase in temperature. Suppose we have a say we have a rod, say steel bar of length L, say initial length L, and suppose it experiences a temperature change of delta T, then there is a, I mean I am exerting here, it will not be that much. So, this is the change in length delta L, okay, and this change in length delta L is actually proportional to the temperature change delta T and the initial length L, and this is equal to alpha into delta T into L, where alpha is the coefficient of thermal expansion. Okay. Therefore, we can write as this delta L by L is nothing but the strain change in length by initial length is equal to alpha into delta T. Okay. So, what is the strain induced because of delta T is decided by what is the alpha, which is the property of that material, which is known as coefficient of thermal expansion. Now, this relation is linear only over a specified range of temperature. If you really want to see the wide range of temperature variation, it may not be linear. Okay. Similarly, suppose there is a of course, I mean a material like steel is not sensitive to moisture, but there are like say polymer, it is sensitive to moisture, there are porous material which are sensitive to moisture. Similarly, the strain induced because of so this is thermal, strain induced because of moisture is similarly given by beta into C, where beta is the coefficient of hygroscopic expansion and C analogous to change in temperature, C is the moisture concentration, which is the ratio of mass of the moisture in unit volume to the mass of the dry material in unit volume. Please note that because this is strain, this is unitless, therefore, this is also unitless, unlike here unit here is per degree Celsius. Okay. Now, this is actually written here that alpha epsilon I T is equal to alpha delta T for I is equal to 1 2 3 and is 0 for I is equal to 4 5 6. In 3 dimensionals we have 6 strains, 3 normal strains and 3 shear strain, just to show here that if you take a 3 dimensional object and it is subjected to suppose a temperature change of delta T, that will lead to alpha 1, alpha 2, alpha 3, that means which is equal to epsilon or epsilon 2, epsilon 3, which is equal to alpha into delta T, and there is no shear strain. Okay, because due to delta T there is no shear strain. Similarly, here also if there is a moisture absorptions, there will be 3 normal strain because of this and there is no shear strain. Okay. So, alpha is the coefficient of thermal expansion, it is per degree Celsius, you may write this as millimeter per degree Celsius, and coefficient of the coefficient of hygroscopic expansion is actually unitless. Okay. So, now having understood this, let us revisit again what we talked about the residual stress. Now, in a fiber reinforced polymer matrix composites, suppose you have I am just exerting this, say this is a fiber, okay. This is a fiber and this is a matrix polymer. Suppose both experiences delta T. Now, the coefficient of thermal expansion of fiber is much less compared to the coefficient of thermal expansion of matrix, meaning for delta T this fiber will have this much expansion and the matrix will have, I am exciting, it may not be that much, but just to show that this is more than So, this is what is the, because the the coefficient of thermal expansion of matrix is more compared to that of the fiber, therefore, its change in length will be more. Now, consider this fiber and the matrix perfectly bonded, which is the case in a lamina. Now, these are perfectly bonded, okay, and they experience the same delta T. Now, what will happen, because they are perfectly bonded, therefore, they will have same expansion, which is actually less than that of the free expansion of the matrix, but more than that of the free expansion of the fiber. So, this is the expansion. So, free expansion of fiber is this much, free expansion of the matrix is this much. So, what happens is the fiber experiences an additional strain epsilon f, okay, and the matrix experiences an additional compression strain epsilon m. Therefore, the fiber is actually experiencing a tensile stress. If E f is the Young's modulus of the fiber, so this is the tensile stress in the fiber, and the matrix experiences a compression stress, which is, so this is the residual stress. So, there is a residual tensile stress in the fiber, there is a residual compression stress in the matrix because of the mismatch in coefficient of thermal expansion of the fiber and the matrix. So, this is why a residual stress are induced. This is the effect of having change in the temperature change in a fiber reinforced polymer matrix lamina composite. Now, the same is also true for moisture content also. The coefficient of moisture expansion in fiber and coefficient of moisture expansion in matrix are different. Fiber is almost insensitive to moisture, but the matrix is sensitive to moisture, therefore, there will be residual stress similar to this. Okay. Now, having understood that having revisiting the thermal expansion and moisture expansion for isotropic material, we will extend this to fiber reinforced polymer matrix orthotropic lamina. Okay. Now, coefficient of thermal expansion and coefficient of hygroscopic expansion of fibers are vastly different from those for the matrix, just now we have discussed. Okay. They are different, and as a result the hygrothermal strains in lamina are different in longitudinal and transverse direction. That means, if you have a lamina, these are the fiber direction. Okay. Now, if it is subjected to delta T, unlike isotropic material, the strain will be different along 1 and strain along 2 will be different as a result of the sum of the transverse direction things are actually matrix dominated, whereas in the axial direction is fiber dominated. Okay. In addition to that, I am just trying to emphasize the difference with the isotropic material. Some fibers like carbon fibers have negative coefficient of thermal expansion along longitudinal direction. Okay. But in the transverse direction it is positive. Okay. And that leads to the possibility of designing composites with 0 coefficient of thermal expansion. I will come back to this little later when we actually will see this actually in micromechanics. Now, we are discussing everything under macromechanics, where we are not considering the fiber and the matrix as different identity. In a lamina, we are considered the lamina to be kind of homogeneous, but we will discuss this, that because the fiber and matrix properties are different, and because that for some fibers the coefficient of thermal expansion in the longitudinal direction is negative, that leads to the possibility of designing composites with 0 coefficient of thermal expansion, which is very important. Many times it is desirable, okay, especially when we want to have the dimensional stability in a wide range of operating temperature. Now, similar to isotropic material, we can write that the thermal strain epsilon T is equal to alpha I delta T. Only difference here is now we have written alpha I, okay, because like other properties, coefficient of thermal expansion of a lamina is also different in different directions. Therefore, where I is equal to 1 2 3 and this is 0 for 4 5 6, meaning again like isotropic material, here also it does not lead to any shear strain. That means, if you apply delta T, it will only have strains, normal strains, okay. It does not lead to any in plane shear strain and distortion, okay. So, therefore, it is 0. Similarly, the hygroscopic strain is beta I into C, where beta is the coefficient of moisture expansion or hygroscopic expansion, and again beta 1, beta 2, beta 3 are different, and it also does not lead to any shear strain in the, because we are discussing in the material axis. Okay. So, if we apply delta T here, that will lead to epsilon 1, epsilon 2, okay, epsilon 3, similarly for C also. Okay. But no shear strain. So, this is for in general 3 dimension. Now, if we consider a special orthotropic lamina in the principal material direction for a 2 dimensional 2D lamina, unidirectional lamina. So, this is what it is. That means, the thermal strain alpha I is equal to, sorry, epsilon I is equal to alpha I into delta T. If you expand this, this is what it is, epsilon 1 epsilon 2 gamma 1 2 is equal to alpha 1 alpha 2 into delta T. Similarly, the hygroscopic strain because of the change in moisture content is given by this. Okay. Again, here also you note that because of delta T there is no shear strain, because okay, in an orthotropic material in the material axis, like if you apply delta T, it actually leads to strain in the normal strain in 1 and 2 directions, and that does not have, that does not lead to any shear strain in 1 2, because it is in the material axis. Okay. Just like the stress strain relationship in case of special orthotropic lamina, if you apply a normal stress, that lead to normal strain, no shear strain. Okay. Now, just to have a understanding the typical value of say coefficient of thermal expansion for carbon epoxy, alpha 1 is 0.88 into 10 minus 6, whereas alpha 2 is much higher, you know, this is matrix dominated. Okay. Similarly, beta 1 is 0.09, but beta 2 is much higher, okay, 0.3. Please note that this alpha 1, alpha 2, beta 1, beta 2 are actually function of the coefficient of thermal expansion of the fiber and the matrix. Similarly, beta 1, beta 2 are the function of coefficient of thermal expansion, coefficient of moisture expansion of the fiber and the matrix, and of course, depending upon their relative proportions. But here we are considering the overall property of the lamina. When we study in the micromechanics, we will have a detailed understanding of the influence of the individual properties. Okay. Now, suppose we have a orthotropic, special orthotropic lamina, that means in the material direction. Suppose this is subjected to stresses sigma 1, sigma 2 and tau 1 2. Therefore, the total strain considering the hygrothermal and mechanical is given by this. Okay. The strain is stress into compliance matrix plus, because of delta T, this is the additional thermal strain, and because of C, this is the additional hygroscopic strain. Therefore, the total strain is given by this. Okay. So, you can write this in short, that epsilon is equal to S into sigma, this is in the material axis, okay, alpha into delta T, beta into C. So, now we can write this as S into sigma is equal to epsilon minus alpha delta T minus beta C, and therefore, we can write sigma is equal to S inverse of this. So, this S inverse is nothing but, you know, this S inverse is nothing but Q, the reduced stiffness matrix. So, Q into epsilon minus alpha delta T minus beta C. Again, note that there is no hygrothermal shear stresses or strain in the principal material axis, okay, because it is specially orthotropic. Okay. Now, suppose we have a lamina, okay, and it is unrestrained, that means it is free, there is no restraint here, it is free and it is subjected to say delta T and C. Okay. Now, if it is free, that means there is no stress. Okay. So, if we put sigma is equal to 0 in this, okay, the stress strain relationship, we get that this is the total strain, okay. Alpha delta t plus beta c is the total strain, because it is free to expand. Suppose under it is subjected to delta t and it is free to expand or contract, therefore, there is no stress. Now, suppose it is fully restrained, that means suppose this is the lamina and we completely restrain it, that means it is subjected to say delta t, but it is not allowed to change its dimension. Okay. Then what happens? That means there is no strain, strain is 0. So, we can put epsilon is equal to 0 here and you get the corresponding stress. Okay. Meaning, suppose you have, suppose you will understand this, suppose you have a steel rod and this is a fixed and it is subjected to delta t. If it is not fixed, it would have experienced the strain epsilon is equal to alpha into delta t. Now, this amount of strain is actually restrained, that means it will have the corresponding stress is equal to E into alpha into delta t. What will be the, suppose delta t is, so what will be the stress here? The stress will be compression here, because it is not allowed to expand. Okay. So, similarly, if the lamina is actually restrained, all the strains in all the directions strains are 0. So, that leads to this is the stress. So, we can write this S inverse as Q. So, the stress is equal to alpha delta t beta c. So, you can clearly see that if delta t is positive, then the stress is negative. Okay. If delta t is negative, the stress will be tensile. Okay. So, again note that we are dealing in the material axis and therefore, there is no associated shear strain or stresses, but this is not true if we try to establish the same hygrothermal stresses for a generally orthotropic off axis lamina. Okay. Now, we will see what happens in a generally orthotropic lamina. Now, this is a generally orthotropic lamina. Okay. So, the fiber direction is at an angle of theta with the global axis x y. So, material axis is 1 2. So, suppose this is subjected to delta t. Okay. Suppose you have a lamina and it is subjected to delta t. So, naturally it will expand in x and y directions. So, therefore, there will be corresponding epsilon x and therefore, there will be corresponding alpha x, where alpha x is, where epsilon x is nothing but alpha x into delta t. Okay. Similarly, there will be epsilon y, which is nothing but alpha y into delta t. Now, this alpha x and alpha y are related to the corresponding strains in the similar way like we have done in the material axis. Okay. So, the thermal strain is given by this, okay. And similarly, the moisture or hygroscopic strain is given by this, where beta x, beta y, beta x y are in the global axis. Note that here there is alpha x y and beta x y, which were absent in the material axis. Now, what is the relationship between alpha x, alpha y, alpha x y and alpha 1, alpha 2, alpha 1 2? This is the relationship. It is, they are actually related by the same matrix which relates the strain transformation matrix. Why? Because if you see what is alpha x is nothing but the, it is a kind of, it is the indication of strain along x. Okay. What is alpha y? Alpha is nothing but the indication of strain along y because of delta t. Okay. Same is true for beta x and beta y. Therefore, we can relate the material axis coefficient of thermal expansion to the global axis by the same strain transformation matrix. Therefore, this is how they are related, alpha x, alpha y, alpha x y by 2, because we are using the same transformation as stress transformation is equal to alpha 1, alpha 2 0, and similarly beta x, beta y and beta x y are related to beta 1, beta 2 0. This is the transformation matrix, I think all of you know. So, if you just see how they vary, you can see this is how alpha x, alpha y varies with theta. Okay. So, naturally at theta is equal to 0, alpha x is nothing but alpha 1, at theta is equal to 90, alpha x is nothing but alpha 2. This I mean it is very well understood. Similarly, at theta is equal to 0, alpha y is nothing but alpha 2, theta is equal to 90, alpha y is nothing but alpha 1. Okay. And alpha x y, what is alpha x y? Alpha x y actually shows how much shear strain will be actually induced if it is subjected to delta t. Naturally, it is 0, alpha x y is 0 at theta is equal to 0, because in the material axis this is not there, it is also 0 at 90 degree, but it is maximum at 45 degree. Okay. So, just now we have made a comment that for some fibers actually alpha 1 is negative. That means, if alpha 1 is negative, suppose, that means alpha 1 will be somewhere here, that means as it varies with theta, there may be some theta where alpha 1 will be, alpha x will be 0. Okay. We may find out some theta where alpha x is equal to 0. Therefore, the fact that for some fibers the longitudinal coefficient of thermal expansion is 0 negative leads to the fact that we can actually design composites having say a longitudinal coefficient of thermal expansion as 0. Okay. So, if we now write for a generally orthotropic lamina, so these are the thermal strains if it is subjected to delta T, and these are the moisture strains if it is subjected to moisture content change of C. Okay. And in addition to that, this is the strain because of the stresses sigma x, sigma y, tau x y. So, the total strain in the global axis is given by this. Okay. So, we can write in short that this is the epsilon x y is equal to S bar, where S bar is the compliance matrix, reduced compliance matrix. So, if we can write this as S bar into sigma, of course, in the x y is equal to strains in x y minus alpha in x y delta t minus beta in x y c, and therefore, we can write that sigma x y is equal to S bar inverse into this. Okay. So, this S bar inverse is nothing but Q bar reduced transform stiffness matrix. Therefore, if we know what is alpha x y, what is beta x y, and change in temperature and the change in moisture content, we can actually find out what is the stress induced in the global axis. Okay. So, having understood this, let us I think we will just discuss one or two problems which will make things even more clear. Suppose we have a unidirectional glass epoxy lamina, say this is an unidirectional glass epoxy lamina. Okay. This is a glass epoxy lamina which is heated from 30 degree to 80 degree, that means delta T is equal to 50 degree Celsius. Okay. So, we have to determine the components of stresses and strains associated with the material axis and global axis x y for theta is equal to 45 degree under two conditions. Okay. Number 1, if the lamina is fully unrestrained when it is heated and fully restrained when it is heated, that means in one case the lamina is free, in another case it is fully restrained. Now, we will have to understand what we exactly mean by restrained lamina. Actually, lamina itself is not a structural component, number of lamina are actually stacked together. Okay. And therefore, when different lamina will actually be stacked together, suppose this is one lamina, this is another lamina, and they make a laminate. Now, because this is perfectly bonded, therefore, when this lamina, which may be suppose a 45 degree lamina, when it experiences delta T, it is not allowed to freely expand. So, that is what it is restrained. In fact, in a laminate it is not fully restrained, but it is restrained. Okay. Now, in this case we have it is told that it is fully restrained, okay, and in one case it is fully unrestrained. Now, when it is fully unrestrained, that is free, so there is no stress. If it is free, suppose you have a lamina and it is heated, okay, what will happen? It will expand. There is no restraint, therefore, there is no stress. Okay. So, if sigma is equal to 0, therefore, we can write in the material axis the strains are given by this. So, this is the corresponding strain where delta T is 50. Okay. All these properties are given here, and we can find out the strains in the global axis by using the strains transformation matrix. Mind it, this is actually half, we will have to multiply this by 2 to get the actual strain, okay, into 2 will be the gamma xy. So, this is simple. So, in the material axis we can immediately find out what is the strain, and by using strain transformation we can find out what is the strain in the global axis. Now, in the second case, when it is fully restrained, and subjected to delta T. So, if it is fully restrained, that means there is no strain, and we put this equal to 0 in this. So, what we get is this equation. Okay. So, the strain is given by q bar into alpha x y into delta T. Now, what is q bar? So, if you expand, this is, so how we get q bar, because this comes from E1, E2, nu 1 2, G1 2 and theta. If you remember that we had these expressions for elements of the reduced transform stiffness matrix in terms of E1, E2, nu 1 2, G1 2 and theta, and all these are given here, this E1, E2, G1 2, nu 1 2 and theta is given. So, we can determine this, and therefore, we can find out the stresses in the global axis also. Okay. Next, let us take another problem. A unidirectional glass epoxy orthotropic lamina, actually it forms one layer of the laminate, which is initially at a temperature of 30 degrees Celsius. The lamina is assumed to be initially stress free, that means no residual stress, okay. Fully restrained, the properties do not change due to temperature change, and the lamina does not absorb moisture. What is the maximum temperature that the lamina can withstand according to maximum stress criteria? Now, this is the properties do not change due to temperature, means I will just tell maybe what exactly is that. Actually, when there is a change in temperature, there is change in properties also, we have discussed just now, I mean in the first few slides, okay. But that we are not considering here, as there is a change in temperature, there will be change in E, okay, Young's modulus and other properties, but that we are not considering here, okay. And we assume that it does not absorb any moisture. So, what we need to find out is, it is at 30 degrees Celsius, what is the maximum temperature T which it can withstand without failure using maximum stress criterion. All these data are given, E1, alpha 1, alpha 2, this is alpha 2, okay, and then sigma 1 ultimate this longitudinal tensile stress, longitudinal compressive stress, transverse tensile stress, transverse compressive stress, and then compressive strength and in plane shear strength. Okay. Now, suppose the temperature is T, suppose it can withstand a temperature of T. Okay. We have to find out that. Now, since it is fully restrained, okay, that means since it is fully restrained, that means this equal to 0. So, what is the stress? What is the stress then? Sigma 1, sigma 2, tau 1 2. This is nothing but, we can write this as Q, S inverse is nothing but Q into minus alpha delta T. here there is no moisture concentration also, it is 0. Therefore, this is Q11 bar, sorry, Q11 Q12 0, Q22 0, Q66 okay, into alpha 1, alpha 2, delta T minus. Therefore, sigma 1 is equal to minus Q11 alpha 1 plus Q22 alpha 2 into what is delta T? Suppose T is the maximum temperature it can withstand. So, T minus 30, sigma 2 is equal to minus Q12 alpha 1 Q22 alpha 2 into T minus 30. Okay. And there is no tau 1 2. Okay. So, we have Q1, we have sigma 1, we have sigma 2. Now, depending upon what is the sign of this, we can apply now this maximum stress criterion. So, all these things are known. Okay. This is sigma 1 and this is sigma 2. So, only thing which is unknown is T, all other values are known. Okay. So, this will give us, we can find out what is that maximum T it can withstand okay, for safety. Here also we can find out what is the maximum T we can withstand. Therefore, minimum of these two will be the maximum temperature it can withstand before it fails. Okay. So, we can take the minimum which will be the maximum temperature it can withstand before it fails. Okay. Now, this is another problem where you have a 45-degree lamina which is completely restrained in the x direction. That means, it is restrained in the x direction, this is the x. It can move in the y direction. Okay. All these given E1, E2, okay, nu 1 to G 1 2 is given. It is experiencing a temperature change of 50 degrees Celsius, given that alpha 1 is equal to 0, that longitudinal coefficient of thermal expansion is 0, alpha 2 is given as this. We need to find out what is the stress along x. Naturally, because it is constrained in the x direction, there will be stress along x, it will experience sigma x. Okay. That we have we can clearly understand. So, what is that sigma x? Okay. Now, we have the stress strain relationship is given by this, the strain in the xy plane is related to the stress in the xy plane and the thermal stress, I mean thermal strain. Okay. This is the total strain, because there is no moisture content part is not here. Now, in this case it is given that because if you look at this, so there cannot be any strain along x. However, it can expand in the y direction. Okay. Sorry, yeah, it can expand in the y direction. I mean, it can have strain in the y direction, and since it can it is free to move in the y direction, therefore, there cannot be any stress in the y direction, and there cannot be any shear stress in the y direction. Okay. So, if you look at this, we can write this as sigma x equal epsilon x equal to 0, epsilon y and tau x y sorry gamma gamma x y, this is equal to S11 bar, S12 bar, S16 bar, S12 bar, S22 bar, S26 bar, S16 bar, S26 bar, S66 bar into sigma x. Sigma x is the only non-zero stress and this is 0, this is 0 plus alpha x, alpha y, alpha x y into delta t. Okay. Now, alpha x, alpha y, alpha x y you can get from, you can find out alpha x, alpha y, alpha x y using this transformation matrix alpha 1, alpha 2, alpha 1, alpha 2 is given. Okay. Therefore, if you take the first equation, 0 is equal to S11 bar sigma x plus alpha x delta t. Therefore, sigma x is equal to minus alpha x delta t divided by S11 bar. So, where from we get S11 bar? This we get from E1, E2, nu 1 2, G1 2 and theta. Okay. So, we can find out this all these elements of this compliance matrix, and we can also find out alpha x, and we know delta t is 50. Therefore, we can find out what is the stress induced along x, and naturally it is, as you can, as expected, it is negative because it is constrained. Therefore, it is not allowed to expand, therefore, it will experience a negative compression stress along x. Okay. So, what we understood is that we can have the hygrothermal stress strain relationship in the material axis as well as in the global axis. Okay. So, we can find out the strains along the material axis and transform them to global axis, or we can actually transform the coefficient of thermal expansion in the global axis and directly we can find out the strain, meaning that we can, given alpha 1, alpha 2, we can find out what is alpha x, alpha y, alpha x y, and from there we can find out what is epsilon x, epsilon y, gamma x y as alpha x, alpha y, alpha x y into, same is true for hygroscopic also, or we can find out, given alpha 1, alpha 2, we can find out what is epsilon 1, epsilon 2 as alpha 1, alpha 2 into delta t, and from there we can find out what is epsilon x, epsilon y, gamma x y using epsilon 1, same thing. I mean you can take either of these and we can find out the stresses and strain in the global axis. So, since we know what are the defined failure criteria, we can also apply failure criteria for combined hygrothermal stress situations also. Okay. Only thing that the stresses will be linearly superposed, and this is possible because we are working within the linearly elastic range. So, I will stop here today. Thank you.